Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at group problem 7b, which deals with some of the concepts of work, energy, and power, which, as we've discussed, is the rate at which work is done. As always, for the group problem that we will be looking at, copies of the problem itself are located on Canvas, as well as a key with some explanations, if you'd rather use that as a resource. Here in the video, we'll be going through the main parts of the problem and talking through how to set up and solve group problem 7b. So there is a visual that goes along with group problem 7b. If you'd like to have access to that visual, you're welcome to access the key on Canvas. Here I like to have a blank page for us to work, that way we have a lot of space. But if you would like that visual, then you're welcome to use it. So I'll read us a bit of the context for group problem 7b and then we will get started. Our problem statement says this: you've been hired to help design a roller coaster for an upcoming theme park. There is limited space for the roller coaster and the plan is to be similar to the drawing above. Essentially, we'll have what looks like a hill that will take riders up, the riders will come down, and then back around. There is a darkened portion on the track. That is where the roller coaster car will be slowing down. We're told that the distance that the cars have to slow down is 250 meters. The roller coaster cars load up at the beginning of the ride, about right in here, and then they're pulled up a hill by a motor, which will be a bit of what we are focusing on. At the top of the hill, they are momentarily stopped before the cars begin traveling down the hill, and they are brought to a stop at the end of the braking track in here. We are told that the force of friction on this portion of the track is 64,000 newtons. Probably a large amount of force in order to slow down a very large object here. We are told that the roller coaster car has a mass of 20,000 kilograms. Again, that number might seem a bit high, but remember we're looking at probably a big object, very large, along with a lot of people on that object. Right? It's probably made of some type of steel or a pretty durable metal. So there's probably going to be a very significant mass along with that object. For the purpose of this design, we can ignore air resistance and friction anywhere else besides on the braking track, where we will look at the force of friction. So the first thing that we're going to do here is, well, kind of get an idea of what we're looking for. There are two things that the problem is going to ask us to find. One of them is the height of the hill that we can design for based on what we know about the other parts of the track. And the other part is, this circle here is what's called a drum motor. It's a type of motor that can be used in this type of roller coaster design. And we want to know how much power that motor needs to have. Now, to work our way back there, the first thing that the problem wants us to find is, what is the work done? Because remember, work is a part of this idea of power. Power is the rate at which work is done. But we want to find the work done on this portion of the track, the braking portion. Now, we have two ways of finding work. One, work is equivalent to a change in energy. Or two, work is equivalent to a force multiplied by the displacement of the object as it experiences that force, multiplied by cosine of the angle between the force and the displacement. Now, based on what we're given here, we can probably assume in that portion of the track we're just going to be looking at the kinetic energy of the car, but we don't really know anything about velocities, so we can't really find anything with the kinetic energy yet. But we are given a force and we're given a displacement, so this approach is probably going to be a good one. The absolute value of 64,000 would just be 64,000 newtons, and 250 meters, absolute value is just 250 meters. Now the angle between them, well, we can assume our roller coaster car, if it starts here, goes up the hill and down, right? The roller coaster car is probably moving to the left on the track. And as we've talked about really all year, friction is a force that opposes or resists sliding. Which means we can probably assume that the force of friction is acting against the displacement of the object, against its direction of motion. So, if our force is to the right, and we're moving to the left, the angle between those would be 180. So, cosine of 180 degrees. So now we have enough information to solve for the work being done, 64,000 multiplied by 250, multiplied by cosine of 180. Now we're going to get a very large negative number here. It looks like negative 16, if it's going to be 16 million. Yes. Joules. Now that number seems very, very large, but remember, we're taking an extremely heavy object, this roller coaster car, a mass of 20,000 kilograms, and we're removing all of its energy. Probably has a lot of energy as it's moving around the roller coaster. Now our number here should be negative because our object is losing energy. Remember, work is a vector, meaning work can be negative. That doesn't necessarily mean the energy is negative, it just means our object loses energy. Now, moving on to the next portion of the problem, we're then asked to find what would the velocity of the car be as we're going into this section. Now, this is going to be about part 3 of the group problem. Now, the other way we look at work is we can look at work as equal to the change in energy of our object, which would be the final energy minus the initial energy, right? Now, at the final point, at the end of the braking track, we can assume our car is going to be stopped and we're on the ground, and we're also not told anything about a spring here. So we can assume that value is probably going to be 0. Now, the initial energy we have, before we get into the braking track, so like right in here, we can probably assume all that energy is kinetic energy. Why is that a good assumption to make? Well, we're on the ground, so our gravitational potential energy should be 0, and there are no springs here. So this work done, negative 16 million joules, is actually going to equal our initial energy, which all should be kinetic energy. Remember, we technically have 0 minus this initial energy, so there should be a negative here. Now, mathematically, if there's a negative on both sides of our equation, we could divide by a negative or divide by negative 1. So what I'll do here is I'll kind of do that just to show that we're now here. 16 million joules is equal to our initial kinetic energy, which we know is equal to 1/2 mv squared. So now we want to set up our scenario to find a velocity. So 16 million joules is equal to 1/2 multiplied by, go to 1 there, when I went to run into 2. 1/2 multiplied by our mass, 20,000 kilograms, multiplied by v squared. Now, I would do a little bit of mental math here. 1/2 multiplied by 20,000 is just going to be 10,000 kilograms. And then I would need to divide by that value and then take a square root to get our velocity term by itself. Let's divide both sides of our equation by 10,000 kilograms. 10,000 over 10,000, those will cancel out. We'll take 16 million divided by 10,000, and I get a value of 1,600 is equal to v squared. And as we mentioned, we then need to take a square root to get a velocity of 40 meters per second. Okay, so now we've been able to use the idea of work, using our work and force equation, and then our connection of work to changes in energy to find our initial velocity. Now, that's going to tell us what's going on right here at this portion. But we want to take that idea and try to figure out what's going on here to find the height of the hill, because that ultimately is going to tell us how much power we need to get our roller coaster car up that hill. Right? We need to know how high the hill is in order to figure out how much power we need to get that job done. Now here, let's say that the point at the hill is one point that we're going to compare to this point in here. The energy, let's say at the top of the hill, we'll call that the initial point of our 2, and the energy at the bottom of the hill, we'll call that our final point of the 2. Now again, initial and final can be applied to really any 2 points that we choose. We're saying initially, we're going to call that the top of the hill, and finally will be the bottom of the hill. Now, because we're assuming that there's no air resistance, and on this portion of the track there's no friction, we can assume that Well, the energy at the top will equal the energy at the bottom. It's the idea of energy conservation. As long as as long as we are dealing with conservative forces here, right, not things like air resistance or friction, then we can assume our energy doesn't change. So what I'm going to do here is I'm going to set the energy initial equal to our energy final. You oftentimes might have seen me write the equation this way. Energy at our initial point is equal to our energy at another point. Right? It's the same idea as of energy conservation. Now initially at the top of the hill, we're told that our car does come to a stop, so no kinetic energy, and there are no springs here, so at the top of the hill, all of our energy would be gravitational potential energy. Now once we've reached the bottom of the hill, we can assume we're on the ground, and again there are no springs, so at the bottom of the hill, all of our energy would be kinetic energy. Now since we know the velocity involved here, I can find what this kinetic energy would be. 1/2, 20,000 kilograms, and 40 meters per second quantity squared. So here we go. 0.5, 20,000, 40 squared. We get a number that actually looks familiar, 16 million joules. That is the kinetic energy we have at the base of the hill. Now that must equal our initial gravitational potential energy, mgh. So in order to get h by itself, I need to divide by m and g. I'm going to put some numbers in here to make that a little bit easier. Mass. Sorry, the board is very sensitive today and seems to want to be registering touch all over the place. So if you see these little dots in here, sometimes that's what the touch is. So 20,000 kilograms. 9.81 meters per second squared, and h, mgh, is equal to 16 million joules. A lot of big numbers here. So first I'll take m and g, I'll multiply those together. 20,000 multiplied by 9.81. So that's going to give me 196,200 multiplied by h is equal to 16 million. Now I'll divide this value, 196,200. So 16 million divided by 196,200 gives me about 81.54, and that would be a height. So our unit here should be in meters, because we did use our standard units here. So in order to get that height, really what we did was we applied our idea of energy conservation. Assuming that we're dealing with conservative forces, so we're ignoring things like air resistance and friction, the energy we start with at the top of the hill should be equal to the energy that we end with at the bottom of the hill. At the top of the hill, all the energy would be considered to be gravitational potential energy, no springs and we're at rest. At the bottom of the hill, all of our energy would be considered to be kinetic energy, no springs and we're on the ground. So then we can use these ideas to find our height, 81.5 meters. Now that was one of the two questions we wanted to solve. The other question was, how much power do we need? Now at this point, power, as we've talked about, is really a rate of work done as a function of time. Now another way that we've expressed power is work is a change in energy. So power can also be expressed as a change in energy over time. Now at this point in the problem, you're going to be given three different motors. Motor A, motor B, and motor C. Each of them have different power outputs, and each of them also have a different cost associated with them. Right? So, if we want to find, and what the problem is going to push us to is to find the time it would take each motor to get our roller coaster car up the hill. So if I rearrange my equation a bit, I can multiply time up to my numerator. I can divide by my power variable. And then multiply time up here. So power over power, that would cancel out. Time over time, that would cancel out. I get something like the time would be equal to the change in energy, or the work, divided by the power. Now, if we look at the change in energy here, well, the change in energy goes from no energy, just starting at rest on the ground, to a lot of gravitational potential energy, let's say at the top of the hill. Now, that amount of energy is the same energy that we have at the bottom of the hill, which should still be 16 million joules, right? That's the energy we need to get up to this height. It's the energy we have, right, once we get down to the braking track, and it's the energy that our force of friction takes away at the end of our problem. So then we should have 16 million joules of energy is what we need to get our roller coaster car up the hill. We would then divide by how much power our motor is able to supply. Let's say this is for motor 1, so 230 kW or 230 kilowatts. We multiply that by 1,000, this would be 230,000 watts. So we've got 16 million divided by 230,000. I get about 69.6 seconds. This would be roughly how much time it would take our this motor to get our roller coaster car up the hill. Now, as you can guess, if we have more power in the motor, that means we're going to do the same amount of work in much less time. Motor B gives us a value of about 45 seconds. Motor C gives us a value of about 25 seconds. In the context of this problem, what I'm asking you all to do is to make a choice. What do you think, if you were the designer, would be an appropriate value or appropriate motor to use based on the numbers that we are given? Remember, as it gives you in the problem, each motor has a different cost associated with it. The more powerful the motor, the more expensive it's going to be. So, as a designer, that would be a point you would need to consider. I can't just go out and choose whatever equipment I want. I have to be mindful of the expenses that are associated with that. So here, hopefully this gets us kind of set up and thinking about the right ideas for group problem 7B, looking at the ideas of work, changes in energy, a little bit of energy conservation, as well as how to apply our understanding of power to make a design decision. As always, you're welcome to direct questions my way if you have them. There's also a hard copy key of this problem on Canvas if that's a resource you're looking for as well. And as always, good luck.